Hi, my name is Shamoon Siddiqui, and today I'll be presenting Medical Transformer, Gated Axial Attention for Medical Image Segmentation. This is a paper by Valinarusso, Oza, Haki Haliloglu, and Patel. This is a relatively new paper. The authors are from Johns Hopkins University and Rutgers University, and it was published less than a month ago on February 21st, 2021. The problem that it covers is that of image segmentation, specifically within the medical domain. Given a medical image, whether it's an MRI, CAT scan, whatever kind of medical image it may be, the goal is to detect lesions, tumors, and other anomalies. One problem with this domain is that the image datasets are limited in size when compared to ImageNet or even larger databases, not like celeb databases. So given the relatively small image dataset, training becomes somewhat cumbersome. Existing state-of-the-art previous to this paper mostly involved convolutional neural networks. One of the issues that this paper uncovered is that convolutional neural networks do not have any global context, and they apply filters locally, patch by patch. A problem shown in this image is that missing areas, as shown here on the right, can be mistaken for a masked segment, tumor, lesion, etc. The med transformer or medical transformer, the med-T that they developed, uses an attention layer, which is a gated axial attention layer, which modifies the tensor to focus on attention in one axis at a time. One of the other innovations here is the two branches for the model, one that they call the local branch and one is the global branch, shown here in the diagram. The encoder uses one-by-one convolutions shown here, and similar to the canonical transformer, passes it through an attention mechanism, which here is the gated axial attention layer, does a norm and does it again per encoder block. We see that in the global and the local, we have a encoder-decoder mechanism. The difference in the global is that we don't go down quite as small, so that we can maintain that global context. The data sets that they use are the brain anatomy segmentation, which contains 1,300 scans for training and 300 for testing, gland segmentation, which uses microscopic imaging, and MONU-SEG microscopic, which is microscopic data set as well. So one thing to note is that these are very limited data sets with just a handful of images. So their core innovation here of local global training. Typically in convolutional neural networks, it's done patchwise, which is much faster than processing the entire image because each patch is a smaller size, 9 by 9, 16 by 16, whatever the patch may be. But one of the problems we have is that the segmentation mask itself may end up being larger than the patch itself, which means that if you are training in a patchwise regime, you don't understand the relationships between those patches. In the global branch, as we saw before, there's one-by-one convolution in the encoder block, which captures the entire image and allows for this local global training as well. One advantage of a transformer over previous state-of-the-art in any domain is that transformers are able to use potentially fewer parameters. So within medical imaging, the U-Net has been a popular go-to model for image segmentation. And you can see here that the U-Net that they've described here has 3.1 million parameters. A straight fully connected network, 12 million parameters. And we continue to go down with modifications of the U-Net with the res blocks and various other forms of the U-Net. Whereas within med-T, we are at 1.4 million parameters. So it is not the smallest model, but it is comparably smaller than some of the much larger ones, like the fully connected, the U-Net, and the res U-Net. Now the results are measured either using the F1 score or I over U, which is section over union, where higher numbers are better. So fully connected network, as one would expect, depending on the data set, does not do all that well. Specifically in the MONU-SEG dataset, fully connected performs poorly. The UNet convolutional architectures perform better, and within MoNuSeg, it's substantially better, but within the brain, it's not that much better. And then down we go to the axial attention UNet, which is a fully attention mechanism similar to the one described in this paper, which continues to do better. And finally, in the proposed architecture of the MET transformer, they split it up with looking at just the gated axial attention mechanism and the local global training, and both perform well, but both together perform even better. So, in conclusion, this paper introduces a way to do medical image segmentation with a transformer architecture. It utilizes gated axial attention as opposed to standard self-attention, and utilizes local global training. So with that, thank you.